Okay, so the solution was to provide a mixture of different widths of the segments because, single segment would be good for short connections. Maybe if you have one or two pass gates along the way, it's not a big deal. But if you're going from one corner of the chip to another corner of the chip, then, 100 or 200 pass gates would significantly degrade the performance. So what I'm doing is I'm showing a cartoonish representation of the routing structure only in one dimension. So these gray boxes would be switch boxes, and I'm ignoring anything that is coming out here or going down here. But I mean, you can imagine that the same logic would apply to that. So basically here I'm showing you three different lengths of the segments. The blue ones start from one switch box, end with another. So obviously there's going to be one diamond in between here, and if you need to make a connection that was that entered this switch box here, then you can make one connection here, another connection here, and maybe goes out here. So you do need three of these, and then this track, right? So this whole line is called a track, which has many of these single segments. Then you can use another part of this track to maybe make a connection that comes in here, goes through these guys, and comes out here. And then you can use these guys, the rest of it for other connections. So basically, the track here can be shared by many connections here. And then, of course, here I'm showing you three tracks that have segment lengths of 1. Right? Now, the red ones are double tracks. So basically what they do is they start from one switch box, skip the one in the middle, so there is no connection here, and they end up here, right? So what you could do with this is to take one route that, for example, enters here, make a connection in the diamond to this. This goes to this track, and then you make another connection here, and maybe get out here, right? So instead of, if you wanted to use the single segment, then you needed to use 1, 2, 3, 4 connections with pass gates in between, but here you only use one pass gate in between these two and make that connection, right? Now the downside of that is you would potentially be wasting some of the track resources that you had. So if and it doesn't show well on the case that you have a segment length of 2, but let's say you have a segment length of 6. So let's assume that all of these are connected, right? So here what you could do is you could use a signal here that comes in here and then gets out here, right? But maybe the next signal that you have in the segment length of 6 comes in here, right? Then it means that even though this is not being used, but you can't use it for this particular signal, which might end up wasting this. You might not use that, right? So that's the downside of it. And of course, I mean, the other question would be the offset of the switches. So here you have track 2 of length 2 that starts on these switch boxes, and then you have another set of track 2 segments that start here. So you could stagger the location of these. And you can imagine that if you have segment length 6s, then if this is of length 6, then you could have something like this, something like this, something like this. So these are going to be different tracks, each of which are hosting these segment lengths of 6 to do that. I'm not showing you any segment length 6s here, but they do exist in some of these FPGA chips. Segment length 4, for example, appears in Altera. Segment length 6 appears in Xilinx. Xilinx doesn't have segment 4. And then you have the long segments here that span the whole chip. And you can imagine that in terms of the load, this is not going to be your friend for signals that need to be fast, but if you need to communicate from one end of the chip to the other end of the chip, then you would use this green one. And again, here I'm showing you the simplified version of it. Each of these resources would have lots of details. So for example, in a segment length of 6, you could enter it from the end and get the output there, but you can also tap it in the middle. So this could enter the signal, and then at offset 3 it could get out the data or even get in the data, and then you could have this. But again, I mean, these are the things that you can read in a data sheet and understand the details. So um, I'm omitting those and basically conveying the basic concepts of FPGAs. Um, all right, and then the other question would be, do you have a hierarchy of connections? So some of the Altera FPGAs, for example, have explicit hierarchical routing connections that you will see later in these slides. But if you think about it, providing a segment length of 6 in Xilinx chips that are flat is essentially a hierarchy, right? I mean, if you're skipping a bunch of connections, then in some sense you're doing something similar to a hierarchical connection. So I don't see a major difference between these two. To me, they're the same. And over the time, Xilinx and Altera have sort of converged to somewhere in between the hierarchical connections and the flat connections. The important thing is that you have to have a dictionary of the delay that each of these segments is going to incur, and you have to have routing algorithms that say, if for example you want to go from here to here, then you have to go through these switch boxes to get there, and you don't, for example, have a direct connection. Later on, Altera added some direct connections to sort of cheat the hierarchy tree, and that means it's more and more close to Xilinx. Same with Xilinx. Xilinx used to uh, basically make these connection boxes from the logic, go through some of the switch boxes, and then to other ones. Sorry, go through connection boxes, switch boxes, then to other logic. But then they provide a direct connection to those, and that in some sense is similar to what you have in a hierarchy. In terms of how to populate the switch boxes, obviously if you want to provide full flexibility, it's going to be very expensive. So each of these connections, remember, does require a switch to make it happen, and switches take area, silicon area, so you don't want to do that. And this is the Wilton switch, which is very common in FPGAs. There are some other switch architectures as well, like Imran switch and so on. And basically the way that people came up with these switches was to run Dijkstra algorithms on the proposed architecture, proposed routing topology, and see which one gave you the best across these, say, 20 benchmarks. So basically it was very simulation intensive. Now, there has been some work that does analytic optimization in later years, but those tend to be hairy. So people rely a lot on running experiments and seeing which one of these is the best one. Now, in terms of the modern FPGA architectures, take these basic elements that I talked about and look at some of the underlying details of them. And again, VirtexII is an old chip by now, but I need to talk about VirtexII now so that I can later on talk about VirtexVI and so on. So because these architectures seem to be incrementally getting more and more complex. So if you understand VirtexII, there are less issues that you have to deal with, and it doesn't become too overwhelming. So basically in VirtexII, what you have is you have a lookup table here, right? And that lookup table could have a D flip-flop or latch, and you may or may not use that in your connections. Okay, so you could get the output of this combinational logic from the lookup table directly out, or you could pass it through this and get the pipelined versions or flip-flopped version of it. And then the other thing that you have here are a bunch of multiplexers that are used for doing carry chain. So very early on, FPGA designers realized that if you provide the lookup table, it's a very good and general platform for implementing functions. But one of the functions that are mostly used are adders. And if you want to build adders using lookup tables by mimicking, XOR gates and majority gates and so on, it's a losing situation. So basically, it's not going to be fast enough. So they provided customized circuit that does the addition. So you could have an XOR gate that does the sum, and then you could have a carry chain that basically takes carry in here and does the carry out. Okay, so you could potentially, depending on how much flexibility the FPGA provides you, you could implement something here like a combinational gate of and or invert logic, and at the same time have a carry logic do this. This may or may not be possible depending on how rich the connectivity inside the lookup table is, but you have to look at different data sheets and how much flexibility you would get. There are some other things like AND gates and so on. So you can see that they came a long way from they came a long way from a simple lookup table to something that has lookup tables, adders, wide input implementations that I'll talk about in a bit, and it's a much more complicated structure. So you can imagine that the synthesis problem, the technology mapping problem, has become much more complicated over the years. And not only that, the lookup table itself. If you remember, the lookup table itself was a bunch of memory elements, right? So people said, why not allow the configuration of the lookup table to act as a RAM? Why can't we put together a bunch of these lookup tables and build larger and larger RAMs? So you could basically do all of that stuff. In terms of the clocks, you have many clock signals that go through the chip, and I'll talk about some of those issues later when we look at even more advanced versions of it. And remember the simple version of the FPGA that I showed you that had an array of lookup tables and then connected to the switch boxes. That is not what FPGAs use today. So the logic block here itself, which is in the Xilinx terminology called CLB, configurable logic block. The logic block itself is made up of I don't want to use the term mini FPGA, but maybe a mini FPGA would be a good term. So one of these is now this whole thing here, and has carry chains. It has the slices, and inside this slice you have lookup tables. So you could have two lookup tables inside one slice, and then you have a switch matrix, which is usually much richer compared to the switch boxes that you have external to the CLB. And the switch matrix is closer to a full crossbar switch that allows connectivity between the lookup tables inside here, and then you could have an output of that lookup table going back to the switch matrix, and maybe take that lookup table's output and feed it as one of the inputs in this slide, and so on, right? And also the connections that go in there, which earlier I called them connection boxes, but they're not necessarily such things in today's FPGAs. So basically the connection boxes, the external connections that come in here, then they have full flexibility or close to full flexibility in connecting to any of the lookup tables that are inside these guys. And also, in terms of the dedicated circuitry, we have adders and multipliers. You could have you could combine all of these guys to make a shift register or make a RAM block. So all of those would show the how complicated it is to program an FPGA, and that's why you rely on the CAD tools provided by these vendors to do the final configuration. And this one shows you a slice which does have now two lookup tables. So you have one lookup table, one 4-input lookup table G, another 4-input lookup table F, and these, in this figure I'm showing you, they have 4 independent inputs, but in more modern FPGAs there could be, for example, 6 inputs coming in. Some of them, 3 and 4 could, for example, be shared between F and G. Right, and these are, all the cost benefit trade-offs that people do when designing these FPGAs to get you the best performance. Now, one other thing that you can do is you could combine F and G by connecting them to another mux. So if I take the output of this and feed it to a mux, take the output of F, feed it to a mux, and then use a fifth input. So if I share the inputs 1, 2, 3, 4 between F and G, and use this fifth signal to choose between F and G, I basically have a 5 LUT, right? So I can combine 2 4 LUTs into one 5 LUT. So take your truth table. 5 would be the most significant bit. So put the upper half of the truth table in G, the lower half in F, and use signal 5 to choose which one of them gives the output. So this is the basic principle of building an 8 LUT out of 6 LUTs that your FPGA might have. And also you have your you have your carry signals and so on that, I don't talk more about it in detail here, and let you guys read through what is on these slides. But essentially what this does is it gives you the specific path for doing additions, right? So if you're using this path of C in, C out, C in, C out of these two slices, then the architecture might put some restrictions on what you can do. So for example, it might say you can only use slice 0 and 1 to do addition, but not slices 2 and 3. So these are the, depending on how many connection resources and programmability the FPGA vendor has put in the FPGA, that could limit what kind of stuff you can do. And this is part of the reason that doing, for example, analytic placement for FPGAs is so difficult, because it's so hard to wrap all of these restrictions into something that is amenable to doing analytic placement. So that's why people have difficulty doing such things and that. And then you could have distributed sum of products, again using these ORCY gates that were shown in the previous slide. So if you have a gate that has 11, 12, 20 terms as a sum of product, then you can hook up a bunch of these slices together and implement it using that. In terms of the routing, the numbers here are the ones that I want you to look at. So if you look at one of these CLBs, they do have direct connections to some of these diagonally to these switch boxes. So there are no longer connection boxes per se as used to be in the old days. And basically one CLB can reach other CLBs using 10 double lines to the right, 10 to the top, bottom, and so on. So 40 in total. They have 10 hex lines. Hex is a connection of 6, and these show that yes, you can tap it in the middle and use it. Same with the double lines. You could tap it in the middle and have the have a single connection, for example. And then you have 24 long lines in horizontal and vertical. So your channel width is pretty large. And remember that these channels are driven by muxes or pass gates followed by buffers. So whenever you're adding more tracks, that means you're using more and more silicon area to implement things. The other things that FPGA vendors started doing was basically follow the same logic as they did for adders. So they realized that yes, if I provide customized addition units in hardware, then people who need to do addition can do it faster. Same thing happened with multipliers. So they added custom multipliers of 18-bit by 18-bit multiplication, and later they provided means of connecting a bunch of these to build wider multiplication. So these multipliers, these embedded multipliers, are much faster than hooking up together a bunch of these CLBs here to implement an 18-bit by 18-bit multiplication. But on the other hand, if you have a design that doesn't use any multipliers, then you end up wasting some of the area, the silicon area that could have been used for CLBs. But again, they have to do a trade-off between what kind of uses people do. And another trick that they have is they provide different variations of an architecture. So if you look at VirtexII, there are some that do have a lot of multipliers. There are some that don't have multipliers or don't have as many multipliers, and customers basically can look at what they need and based on that would order the right part. Now, same thing happened with memory. So even though you can hook up some of these lookup tables and build a memory, which is called the distributed memory, you can also have some embedded memory. So these units are specifically built for doing memory operations, like shift registers, dual port memories, single port memories, read write port memories, and so on. But you can't, for example, do division using them, right? You can't do any addition using these. These are just used for memory. And then added the different stuff like adding unchip serial the deserialization units that do gigabit serial connections and all different kinds of buses for communication to other devices and so on. And well, I don't want to spend time on this slide. Basically has some marketing numbers and so on, and you can imagine that these are dated by now from VirtexII. And the other thing that they did was they started embedding processors in them. So these are actual microprocessors, very simple microprocessors that they put in here, and you could have as many as 4 of these microprocessors in there, and then you can run Linux on this and have some of the more specialized circuit that you want to run faster here. So this could run a regular program, and then at some point in time you need 5 multiplications. Then you can use the multipliers in here to communicate with this. Then you need buses between them and so on. And this talks about the 3 gigabits per second serial communication. Today's FPGAs are much faster, 10 and 20 and so on exist. So this is basically what I have for the basics of the FPGA, and then I'll talk very quickly on some of the slides from Xilinx on one of their modern chips, and also some of the other features that you find in modern FPGAs. But I think even if you stop here, that would give you a good introduction on what FPGAs are and how they are used. I'll also spend some time on the CAD issues that you have, and that would be another video that I'm going to make. Alright, see you later.